Hi, this is Math 2510, and this video is over section 3.5. And we are going to look at deriving the derivatives of trigonometric functions. There are a few things that we have to cover before we get into actually deriving the derivative of sine, and then how we can use that to find all the other derivatives. First thing we have to look at is continuity. Sine x and cosine x. If we look at their graphs again, just to remember, sine x has this wave and it's a continuous function. Cosine similarly has a wave very similar to sine x. It's also a continuous function. So those two functions are both continuous everywhere. Now, tangent, secant, secant, cotangent, well, those functions have certain places where they are undefined. They're continuous everywhere where they're not undefined. So that's tangent, this is cosecant, secant, then cotangent. Okay, so they're all continuous everywhere except for where they are undefined. So everywhere except for where they're undefined. Okay. So when we take the limits of any of these functions as x goes to c, we are just replacing x with c. As long as c is in the domain. So for example, tangent of pi over 2 is undefined. So there is no limit there for tangent of pi over 2. And so we wouldn't have c be pi over 2 there. So all this means is we have to watch out for the places where a trig function may be undefined and not try to find the derivative. At that point, we're going to run into problems and then get wrong. Right, and we'll come back to this because we'll be using that a little later. The next thing we want to look at is what's called the sandwich theorem, or the squeeze theorem. I always like this one because of the funny name to it. But if we have three functions, and f of x, say this is f of x, is less than or equal to g of x, do this as a different color, g of x, maybe like this. So at this point, they're equal. And it's less than or equal to h of x. At this point, it crosses the same point, or touches the same point. But everywhere else, it's greater than if it's not equal to. And if limit, and we'll say this point here is c, the limit as x goes to c of h of x was L, and so that point will be L. And the limit as x goes to c of f of x equals L, so same point. Then the limit as x goes to c of g of x must equal L. If it doesn't equal L, it's below L, well then that will make it below f of x, and that's not true. If it's above L, it will make it above h of x, and that's not true. So if f of x and h of x are equal, and g of x is in between, then they have to be, all three have to be equal and equal to whatever the limit is. Alright, so let's look at sine of x and y equals x. Get rid of these. I could have kept sine of x. Sine of x and y equals x. And we can zoom in on where x goes to 0. And we see, no matter how zoomed in we get, actually, the more we zoom in, the better we see it. I get to zoom in. The blue line and red line match up. You can still see the red line there. Alright, so as x goes to 0, from either direction, sine of x and y equals x are very close to the same function, if not the same function. And remember, if you're dividing two things that are the same, let's say 2 over 2, you get 1. So if sine of x and y equals x are the same thing, when you divide them, it should be equal to 1. So we're going to look at the limit as x goes to 0 of sine of x over x, and say that that's equal to 1. And we're going to prove this. Now we can't prove it by just plugging in 0 for x, because you'll have sine of 0, which is 0, and 0 on the bottom, which is 0, which gives you 0 over 0. And that is, in calculus, that means you have to do a little bit more to see if it's truly 1 or truly 0, whatever it may be. Because this is not it's ambiguity. Alright, so the way we're going to do this is we're going to look at a unit circle. Now, remember that the area of a sector, a unit circle, that's this area here, is equal to 1/2 radius squared theta. That comes important in the very next thing. So we're going to look at the unit circle. We're going to look at a section of it, a sector of it. So this is equal to 1. Actual 1 there. And we're going to label this. I have to make sure I get the labels right. We're going to label this O for the origin. We're going to label this A. And where it comes down, we're going to label that D. Okay. This is going to be our literal triangle. Just this region right here. And the area of that triangle is 1/2 base times height. So base is going to be OD, that line. Height will be 80. Now we have to look at what OD and what AD equal for a triangle. And one thing let me specify is our angle, we're going to deem as x. Okay, so the angle to that line. So if we look at this, I'm going to draw it out here. O, A, and D, angle x. If we look at cosine of x, is going to be adjacent over hypotenuse. Hypotenuse is 1, so it'll be OD over 1. Sine of x is going to be opposite, AD over 1. Okay. So basically, OD equals cosine x and AD equals sine x. So we can rewrite this here, 1/2 sine x, sine x. Now the sector, 1/2 the radius. Radius is going to be 1, since this is your radius of this sector. Radius is 1 squared, and the angle is x. This becomes pi over 2. Oh, yeah, x over 2. That's what I'm going to say. X over 2. Now we're going to look at one other triangle, and this is going to be the bigger triangle. We're going to extend this out. We're going to call that point B. That's going to be point B, and that's going to be point C. Okay. Then we want to look at the fact that OC here equals 1 as well. It's the radius. And we're specifically taking the vertical from that point. Okay, so that triangle is going to have 1/2 OC times BC. Okay. Now OC we already know equals 1. We want to look at tangent. Tangent x, which is opposite BC over adjacent OC. BC OC equals 1. So in other words, BC equals tangent x. So this becomes 1/2. Excuse me. And black, so all three of them end in solid black. 1/2 times 1 times tangent x. And just looking at the picture, we can clearly see the little triangle is less than the sector, which is less than the big triangle. So these areas come first. Little triangle is smallest, sector is the middle size area, and then the big triangle is the biggest. All right, so let's set this up with the equations we have here. So 1/2 cosine x sine x is less than or equal to x over 2, which is less than or equal to 1/2 tangent x. Now, every one of these you're dividing by 2, so we can cancel all these halves. No problem. And then I'm also going to change tangent x to sine x over cosine x. That's just a trig substitution. Now, our goal is to get this sine x over x in the center. So we can take the limit as x goes to 0 of each of these. Because right now, it's just going to be helpful. Want that in the middle. So the first thing we want to do is, since we want x on the bottom, we're going to flip all these fractions. So we have 1 over cosine x, sine x, less the sign flips when we flip these, greater than or equal to 1 over x, which is greater than or equal to cosine x or sine x. Now I'm going to rewrite them. I'm going to rewrite them in the order we would think of. So cosine x over sine x is less than or equal to 1 over x, which is less than or equal to 1 over cosine x, sine x. Just, it's easier to go from lowest to highest. Now we're going to multiply everything by sine. And when we do that, we'll get the sine x in the numerator like we want in the middle. But here we'll have the sine x cancel, so we'll have cosine x less than or equal to sine x over x less than or equal to 1 over cosine x. Right, so now we're going to take the limit as x goes to 0. Each of these. Except for the middle, we'll leave it as the limit of as x goes to 0 sine x over. We'll take the limit of each side. So this comes back to the continuous functions. The fact that sine and cosine are continuous everywhere means that you just plug in the value for that x is going to find the limit. So plug in the value of 0, you'll get cosine of 0 is less than or equal to a limit as x goes to 0 of sine x over x, which is less than or equal to 1 over cosine 0. Oops. Said it, I didn't write it. There. Cosine of 0 is just 1, less than or equal to the limit as x goes to 0 of sine x over x, which is less than or equal to 1 over 1, which is 1. This means now that I'll write here. Thus, limit as x goes to 0 sine x over x. And we just proved this with the squeeze theorem. All right. So we can now go beyond this and prove some other theorems. These will use what we just did. This next one also though becomes helpful because we will use this in the derivative of sine. So the limit as x goes to 0 of 1 minus cosine x. We're going to start by multiplying this by the conjugate. On top and bottom. So when we multiply this, the middle terms drop out. You get 1 squared, which is 1, and then minus cosine squared x. And the bottom don't distribute. We're just going to keep it how it is. And again, we're still taking the limit as x goes 0. I just didn't know it may have need this space. There is a trig identity. Sine squared x plus cosine squared x equals 1. And we can actually manipulate this. So sine squared x equals 1 minus cosine squared x. So we can now substitute the limit as x goes to 0 of sine squared x over x 1 plus cosine x. Then what we're going to do is we're going to break this into two factors without multiplying each other. The first is the limit as x goes to 0 sine x over x. And we'll have the limit as x goes to 0 sine x over 1 plus cosine x. Shoot. Whenever somebody calls me, it kicks me off. erase this as best as I can. Now it decides to save. Oh man, technology. Right. So now I'm gonna since we're on this step. Limit sine of x over x times the limit of sine of x over 1 plus cosine x. Right, now remember, when the limit of a product, limit of f of x times g of x is equal to the limit of f of x times the limit of g of x. So this is allowed. We already did on the left. We know that equals 1. So we only have the limit as x goes to 0 of the 1 on the right. But we can plug in 0. We're not going to get 0 of 0. What we end up getting when we plug in 0 is we get sine of 0, which is 0, plus 1 plus cosine of 0, which actually comes out to be 2 in the bottom. So this whole thing does go to 0, does equal 0. So limit as x goes to 0, 1 minus cosine x over x equals 0. The next thing we want to look at is the limit as x goes to 0 of sine of 2x over x. And we're going to do a couple of these. They're all going to be done kind of the same way, and they're all using the fact that sine of x over x, that limit as x goes to 0. So the way we're going to do this one is we're going to make it look very similar. So we're going to do that by multiplying it by 2 over 2. 2 sine 2x over 2x. And just multiply by 1. Doesn't change anything. And then you can do what's called u substitution. U equals 2x. And so we can rewrite this as limit as x goes to 0 to sine of u over u. Okay. Well, it doesn't matter what u is here. This is just another variable. X and u are very similar. This section here is much like sine of x over x. So we can pull the 2 out in front. And so this ends up being equal to 1. This whole thing ends up being equal to 2. Okay? We can do something very similar to the next one. Limit as x goes to 0 of sine of 2x over sine of 3x. And instead of dividing it by the whole thing by 2, what we're going to do is we're going to I'm going to do this in 2 steps. I'm going to divide top and bottom by x. I'm technically just dividing it by 1. Then the top, I'm going to multiply it by 3 over 3. So I'm multiplying just the, 2 over 2. I'm multiplying just the top by 1, which isn't going to change anything. And then the bottom, I'm multiplying top and bottom of the bottom fraction by 3. So we can pull out the 2 and the 3 that are adjacent to the sign and the signs. So we'll have 2/3 limit as x goes to 0 sine of 2x over 2x and sine limit limit as x goes to 0 sine of 3x over 3x. Both of these limits go to 1. So this whole thing will go to 2/3. And then the last one, limit as x goes to 0 of tangent x over x. We're going to switch tangent x to sine of x over cosine x. Sine of x and x cosine x. And then we're going to break this up, similar to what we did before. Product, limit of a product is the product of the limits. We have limit as x goes to 0 of sine x over x. That is just equal to 1. And then you'll have the limit as x goes to 0 of 1 over cosine x. And that is just going to be equal to 1. So you'll have both equal to 1, so the whole thing is going to be equal. One thing I want to mention in this next thing is this should be a negative sign. I don't even think we use it though, so that's probably why I didn't catch it before. All right, we're going to find that the derivative of sine x now. Now we have everything we need. We're going to have to recall that the limit as h goes to 0 of f of x plus h minus f of x divided by h is our definition of a derivative. That's equal to f prime of x. All right, so we'll use that directly right off the bat. F prime of x is going to be the limit as h goes to 0 sine of x plus h minus sine of x over h. And we have what sine of x equals. So we can write this limit as h goes to 0 of sine of x cosine h plus cosine x sine h minus sine x all over h. We'll have the limit as h goes to 0. We're going to factor out a sine x from the two terms. So the first term is cosine h. Second term, when we factor out from, highlight this, so this term and this term, we get a minus 1. And then we'll have left over cosine x sine h. And the whole thing is over h. Okay. So now what we're going to do is we're going to break up the fraction. We kind of do the opposite of finding common denominator. We want to make this limit as h goes to 0 of sine x times cosine h minus 1 over h plus the limit as h goes to 0 cosine x sine h over h. And then we're going to break each of these up into the products. So limit h goes to 0 of sine x times let me put this in parentheses times the limit as h goes to 0 of, now this one I want it to look like like what we did here. So I do have to factor out a negative sign. I'm going to do that now. Negative 1 minus cosine h over h. And then we'll have plus a limit as h goes to 0 of cosine x times the limit as h goes to 0 of sine h over h. Okay. So this we did first, that's equal to 1. This one we had done second, that's equal to 0, which makes this whole term goes to 0. So now we're left with the limit as h goes to 0 of cosine x. There's no h there, so it just equals cosine x. Like I can't get through this problem without having to save. Alright, so derivative of sine x is cosine x, which is this one right here. Now, we're not going to go through every derivative and how you would derive it. However, I do want to do one more that we won't do it the same way. We're going to actually use what the derivative of sine x is to do this. So we're going to look at the derivative of secant x. And we know the derivative of cosecant x will be the same as the derivative of 1 over sine x, because that's what cosecant x is. And we can do this with the quotient rule. So the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the denominator squared. So the denominator, sine x, times the derivative of the numerator of the numerator is 0, minus the numerator, 1, times the derivative of your sine x, which is now sine x, all over sine squared x. So we'll have 0 minus cosine x over sine squared x. Okay, now we just gotta make it look like what we have here. And so to do that, we can break up the denominator. Negative 1 over sine x times 1 cosine x over sine x. That's going to be equal to negative cosecant x. Okay. So that's how we can do and verify another derivative. So now we have 2 of them figured out. All right, now these derivatives, it'll be good to write them down, keep them with you as you do homework to make sure. Not always going to be easy to memorize. The easiest ones are definitely cosine and sine. Derivative of sine is cosine. Derivative of cosine is a negative sign. The other ones you may have to look up if they ever come up. So what we'll do now will be taking derivatives of some functions that involve cosine, but not only involve cosine and sine and trig function. So first, y equals 3x cubed plus cosine x. Our derivative, you can do each one separately. Derivative of 3x cubed is going to be 9x squared. Cosine x is a negative sine x. All you have to do. Next one, this involves the product rule. So there is a little bit more here. Product rule, you just start with x times the derivative of sine of x, which is cosine x, plus derivative of x, which is 1, times sine of x. This would be equal to x cosine x plus sine of x. For C, this requires the chain rule. And it requires the chain rule. The inside is your x cubed. The outside is cosine x. So that's why it requires the chain rule. So y prime would be 4. We do the derivative of cosine, which is a negative of the negative out front sine of x cubed. And then the derivative of the inside here would be 3x squared. Now 3x squared isn't inside the sign, it's outside of it. So we can multiply the 3 by the 4. Well, we get negative 12x squared sine x cubed, sine of x cubed. Alright, the next one, all of these now are going to require the chain rule. The next one will have sine of 3x plus 5. So derivative of sine is cosine, so we have cosine of 3x plus 5. Hold the inside constant. Take the derivative inside, you get just 3. So I can put 3 out in front. Alright, it's a little bit more harder here. You have sine of square root of 1 plus cosine x. So we'll do derivative of sine is cosine of the square root. And then the derivative of this is going to require more of the chain rule. Remember, this is the same as 1 plus cosine x to the 1/2 power. So we'll have 1/2 come down. And this would drop to a negative half power. Then the inside of this is just going to be a negative sine x. So now we can kind of put all this together. Negative sine x times cosine of the square root of 1 plus cosine x over 2 times the square root of 1 plus cosine x. Now, these won't cancel. They're in the top radical is in the cosine, so you can't just cancel them. You can rationalize the bottom, so we'll end up with negative sine x. I'll put this on top of the square root of 1 plus cosine x times cosine of the square root 1 plus cosine x all over 2 times 1 plus cosine x. Alright, that's probably as far as you can go with that. Switch color so it doesn't merge. Tangent cubed of x squared plus 3x. 3, that basically x cubed is your outside function there. So we'll have 3 tangent squared x squared plus 3x. And the inside of this is going to be 2x plus 3. Oh, wait, I skipped a step. Hold on a second. Inside of this is your tangent x squared plus 3x. So we gotta do that first. So derivative of tangent is secant squared. We'll have secant squared of x squared plus 3x. Now we can multiply this by what's outside, which will be 2x plus 3. So we can put this all together. I'll distribute the 3. So we'll have 6x plus 9 times tangent squared squared plus 3x of secant squared plus 3x. Alright, that's, I mean, any simplifying past this won't make it necessarily any simpler. So we'll leave at that. Okay, a couple more. 2 minus secant x over 3 plus 4 cosecant x. I'm going to rewrite this. 2 minus secant x times 3 plus 4 cosecant x to negative 1. I'm doing that so it's easier to take the product rule. It's going to require the chain rule as we do this, though. So first we'll keep the 2 minus secant x constant, take the derivative of the harder 1. Q minus secant x. The derivative of this, we'll start with the outside, negative 1 plus 3 plus 4 cosecant x to negative 2. And then the inside, derivative of cosecant x, remember, is a negative cosecant cotangent x. Okay. And that's just one side. Then we'll add 3 plus 4 cosecant x of that constant. Take the derivative of 2 minus secant x, which is just going to be the derivative of a negative secant x, which is secant x tangent x. So negative secant x tangent x. Alright, and we can kind of try to simplify this I'll distribute this the negative sign so I don't have a negative sign out there. Secant x minus 2. Actually, wait, no. Just saw another negative sign. So that negative sign and that negative sign cancel. Don't worry about that. So 2 minus secant x. And then we'll have the 4 outside. Secant x cotangent x. All of this over 3 plus 4 cosecant x squared plus minus secant x tangent x over 3 plus 4 cosecant x. I'm not going to really make this any simpler by doing anything else. Alright. The next one, we're going to do implicit differentiation with sine and cosine. Remember, that's when you take a derivative of y with respect to x, you're going to end up with an x prime there, especially if there's other operations like the y being squared or taking the sine of y. Okay, so the left side we'll do first. That's going to be the product rule. So both x constant, derivative of sine of y is going to be cosine of y times y prime. And plus, well, the sine y constant, derivative of x is 1. We have sine. Then the right side, derivative of cosine is negative sine of x plus y. And then the derivative of the inside here is going to be 1 plus y prime. So now we can isolate y prime. It's going to take some algebra. We'll have to distribute first of a negative sine x plus y minus a y prime sine x plus y. So I distributed the x plus y on the negative side. And this stays the same for now. Okay. Now we're going to add over the y prime on the right. 5x y prime cosine y plus y prime sine of x plus y. And we'll subtract over our sine y. At this point, we can factor out the y prime. And I'll factor out 1 as well, or a negative sign. Sine y plus sine x plus y. Now we just divide over and have y prime solved for. And so we have a derivative. Alright, so we'll do a couple more problems, I believe, and then we'll be done with this section. So here we'll have function x cosine x. We want the derivative, but we want to evaluate at pi over 6. Right, so this is one of the reasons we have to use radians for this, is because you're going to have x's outside the trig functions, and you have to use a radian when you have anything like that. So we have to do the derivative first. That's going to require the product rule. So x times the negative sine of x, that's derivative of cosine, plus derivative of x is 1, cosine of x. Okay, so this becomes cosine x minus x sine of x. Now we evaluate it at pi over 6. We'll have cosine of pi over 6 minus pi over 6 sine pi over 6. Okay. This is something that will be on the unit circle. Cosine of pi over 6 is square root of 3 over 2 minus pi over 6, and sine of pi over 6 is 1/2. So what I'm going to do is I'm going to get common denominator. So I'm going to multiply this one by 6 over 6. Get 6 square root of 3 over 12 minus pi over 12. But I can write it as one fraction. Right? That's the exact value there too. The last one, we have f of x equals x plus sine of x, and we want to know where there's a horizontal tangent line. Horizontal tangent line meaning slope equals 0, or f prime of x equals 0. We're going to take the derivative, set equals 0. Derivative of this, derivative of x is 1, derivative of sine is cosine. We'll set that equals 0. So cosine of x would equal -1. So x would equal pi, 3 pi, 5 pi, all odd values of pi. We can write this as pi plus 2 pi. So we can take, k can be all integers. Just multiply it by 2 pi basically. Add 2 pi every time. So before I end this video, I do want to graph this x plus sine x. And we're going to zoom out. And we can see, and let me test this actually, is that we can actually just put in 2 pi. Actually, no, instead of pi. and it will put the pies on the screen. So we can see everywhere there's a pi, this graph goes horizontal. Well, everywhere there's an odd pi, will be up here, right on the line. It even goes negative. It could be negative pi, it's fine on the line. It's an interesting kind of graph too. But it happens to have a horizontal tangent line at every odd interval of pi. Alright, I'll see you in the next video. Bye.